Welcome to Manimated AI. In this video, we'll learn what eigenvalues and eigenvectors are, and see them visualized step by step to truly understand how they work. Welcome to an exploration of eigenvalues and eigenvectors, fundamental concepts in linear algebra. Eigenvectors are special directions that remain unchanged during a transformation, even if they get longer or shorter. Eigenvalues tell us exactly how much these vectors stretch or shrink during the transformation. These concepts are crucial in many fields, including system stability analysis, quantum physics, and machine learning. Mathematically, we express this relationship using the equation AV equals lambda V, where lambda represents the eigenvalue. Let's visualize these concepts to better understand how they work. Let's look at a concrete numerical example. Here, we have a transformation matrix A that we'll use to illustrate the behavior of both eigenvectors and non-eigenvectors. Notice that our matrix is displayed on the left and our mini-coordinate system is set up to clearly show how vectors change under this transformation. First, we consider a vector that is not an eigenvector. Here, we use the unit vector along the x-axis, vector w equal to 1 and 0. Notice how this vector is initially aligned with the x-axis. When we multiply this non-eigenvector by the matrix A, both its direction and length change. This behavior confirms that it is not an eigenvector. Eigenvectors, as we will see, only scale without changing direction. Then in comparison, let's look at our first eigenvector and see what happens when we multiply it by matrix A. Watch the multiplication process step by step. The animation shows the detailed multiplication process, where every term is calculated. The result is exactly 3.00 times our original vector. This scaling factor is our eigenvalue. Notice how the direction of the eigenvector remains unchanged. Only its length scales by the eigenvalue lambda. Now let's look at our second eigenvector and its multiplication process. When matrix A multiplies eigenvector V2, the result is simply lambda 2 times V2. This confirms that V2 is indeed an eigenvector since its direction is preserved and only its magnitude changes according to lambda 2. To summarize, this numerical example clearly demonstrates the key property of eigenvectors and eigenvalues. A non-eigenvector, when transformed by matrix A, changes both direction and length. In contrast, the eigenvectors maintain their direction and are simply scaled by their corresponding eigenvalues. This relationship is captured by the equation AV equals lambda V, which is fundamental to understanding linear transformations. For more intuitive understanding, we begin with a standard coordinate system, complete with clearly marked axes and an evenly spaced grid. This familiar setting provides a reference frame for all our upcoming transformations. To illustrate how typical vectors behave under transformation, we add two random vectors. Notice one vector, shown in blue, and another, in green. Their initial positions and directions are arbitrary, serving as examples of general vectors in the plane. Back to our transformation matrix A. This matrix encapsulates the linear transformation we are studying. Every vector in our plane will be multiplied by this matrix, and we will observe how that multiplication alters their direction and magnitude. Watch closely as we apply the transformation x to x. Notice how the grid itself deforms. Squares become parallelograms, indicating the global effect of our matrix. Simultaneously, the random vectors also change, both in their lengths and orientations. Observe that these typical vectors change dramatically. They rotate and stretch differently. This is the expected behavior for most vectors under a linear transformation. Now, Let's search for those special directions. The eigenvectors. Unlike the random vectors, eigenvectors maintain their orientation under transformation and only scale in length. Let's rotate a vector and watch how it transforms for most directions. The transformed vector differs from the original. However, when the transformed vector points in the same direction as the original, even if scaled, we've found an eigenvector. In those moments, the vector's direction is preserved while its magnitude changes. These are our eigenvectors, the special directions we found where vectors maintain their orientation. Watch how each eigenvector scales by its eigenvalue. The first eigenvector scales by 3.00, and the second eigenvector scales by 1.00. Interestingly, the reverse directions of our eigenvectors also maintain their orientation under transformation. These reversed vectors are also eigenvectors with the same eigenvalue. Because the eigenvalue equation A, v, equals lambda, v, still holds true, just like their positive counterparts, these reversed eigenvectors scale by the same eigenvalues. The first eigenvector and its reverse both scale by 3.00. This is because multiplying by -1 doesn't change the eigenvalue relationship. Similarly, both the second eigenvector and its reverse scale by 1.00. The negative direction is just as valid an eigenvector as the positive direction. This symmetry reveals a fundamental property. Eigenvectors come in pairs of opposite directions. Each line through the origin in an eigenvector direction represents a one-dimensional eigenspace, where every non-zero vector along that line is an eigenvector with the same eigenvalue. This relationship is captured perfectly in the eigenvalue equation. A versus equals lambda v. The transformation of an eigenvector is simply a scaling by its eigenvalue. Now let's explore how to find eigenvalues and eigenvectors mathematically. We start with our familiar matrix A. We start with the fundamental eigenvalue equation, A times vector v equals lambda times vector v. Next, we introduce the identity matrix I to better manage the scalar lambda. We rearrange to bring all terms to the left-hand side, factoring out vector v. For the equation to have non-trivial solutions where vector v is not 0, the determinant of a minus lambda I must equal 0. Let's look at what lambda times the identity matrix means. Now we subtract lambda I from our matrix A, giving us a matrix with lambda terms on the main diagonal. To find eigenvalues, we calculate the determinant of a minus lambda I and set it equal to 0. Computing this determinant, we multiply diagonals and subtract products of off-diagonal elements. Simplifying this expression, we get a quadratic equation in lambda. Solving this quadratic equation, we find our eigenvalues are lambda equals 1 and lambda equals 3. Now, to find the eigenvector corresponding to lambda equals 3, we substitute this value back into our matrix equation. We get a system of homogeneous linear equations. Simplifying the coefficients, this gives us two equations. Solving this system, we find that v1 equals v2, giving us the eigenvector direction of 1, 1. Similarly, for lambda equals 1, we substitute and solve. Again, we get a homogeneous system. After simplification, we get a single independent equation. Solving this, we find that v1 equals negative v2, giving us the eigenvector direction of 1, negative 1. Let's verify our solutions by checking that A times versus equals lambda times v for each eigenvector. In summary, we've found that our matrix A has eigenvalues 3 and 1, with corresponding eigenvectors 1, 1, and 1, minus 1. These eigenvalues and eigenvectors completely characterize the behavior of the transformation, represented by our matrix. Now let's explore the important relationships between eigenvalues and two key matrix properties. The trace and determinant. The trace of a matrix, which is the sum of its diagonal elements, equals the sum of all eigenvalues. For our matrix, the trace is 4, and indeed, our eigenvalues 3 and 1 sum to 4. Similarly, the determinant of a matrix equals the product of all eigenvalues. Our matrix has determinant 3, which is exactly the product of our eigenvalues 3 and 1. Now, let's visualize what different types of eigenvalues mean geometrically. The sign and magnitude of eigenvalues tell us how the transformation affects space. When all eigenvalues are greater than 1, the transformation expands space in all directions. Vectors get longer, and areas increase. When one eigenvalue is greater than 1 and another is between 0 and 1, the transformation stretches space in one direction while compressing it in another. This creates a directional distortion. Negative eigenvalues indicate reflection along with scaling. The space flips across the axis corresponding to this eigenvalue, changing orientation. When eigenvalues equal exactly 1, lengths and areas are preserved in those directions. This is the case with rotations and the identity transformation. When eigenvalues are complex, the transformation includes rotation. The real part determines scaling, while the imaginary part controls rotation. This often occurs in dynamic systems exhibiting oscillatory behavior. In summary, eigenvalues tell us how a transformation affects space. Values greater than 1 cause expansion. Values between 0 and 1 cause contraction. Negative values cause reflection, and complex values cause rotation combined with scaling. The values of eigenvalues have profound significance in applications. In system stability analysis, eigenvalues with magnitude less than 1 indicate stable systems in data science. Eigenvalues represent variance along principal components. In quantum mechanics, eigenvalues correspond to observable measurements. And in mechanical engineering, they relate to natural frequencies of vibration. Understanding eigenvalues and eigenvector gives us deep insight into the behavior of linear transformations. Quick rewind. Here's what we covered: what eigenvalues and eigenvectors are visually, how they work, and why they matter. Up next, we will tackle real examples so you can truly master the steps to solving them. Thank you for watching. Don't forget to like, share, and subscribe, and we will see you in the next episode. Stay tuned. This video is made by Astha Joshi. Keep learning, and I'll see you in the next video.